Thank you. So without further ado, let's talk about the real star of the show, DOM clobbering. So today I will be presenting everything you wanted to know about DOM clobbering, but were afraid to ask. So web applications today accept and process plethora of user input. And they have become a digital playground for users to input their thoughts, feelings, or their favorite cat pictures in more ways than we have ever thought possible. And this ranges from social media applications like Gmail, GitHub, Trello, and many more. And of course, user input can go rogue. And since the early days of the web, developers have been trying to tame this wild west of user input. So the question is, are we validating all these inputs properly? And what could possibly go wrong if we fail to do so? Well, as for the client-side security, the holy grail threat is arbitrary client-side code execution, which is traditionally achieved by injecting malicious JavaScript code into vulnerable pages, also known as cross-site scripting that you see in the previous talk. And what is cross-site scripting? So a short recap, attacker prepares a malicious URL and then shares this URL with the victim. The victim is subsequently lured into clicking this crafted URL by the attacker. And upon completion of the page load, the attacker's code or the attacker's payload in the URL will be executed within the context of the web page in the user's browser, and we will have arbitrary code execution. And this can have various security implications ranging from account takeover to sensitive information leakage, to name only a few instances. Now, XSS is a well-known threat, which is often achieved by code injection and mitigated by controlling or disallowing code execution. So robust XSS defenses are well known, ranging from input validation, trusted types, to HTML sanitization. And Ben, who is now here also in the audience, asks, OK, what about CSP? CSP can also mitigate cross-site scripting, as we saw in the previous talk. Well, of course, if developers manage to roll out a meaningful CSP, it can disallow cross-site scripting cases that occur due to code injection. But actually, what if codeless HTML can cause arbitrary code execution? And how is this even possible? Well, unfortunately, the growth of the web technology has introduced unforeseen interactions between JavaScript programs and their browser-based runtime environment. The research community has only recently started exploring these interactions, mainly focusing on small code and snippets that react to injected markups, which are known as script gadgets. Now, script gadgets are only tip of the iceberg, and other complex interactions exist that attackers can abuse to hijack the program execution and again obtain arbitrary client-side code execution, our holy grail threat. And one of these unforeseen interactions is called DOM clobbering. And let me show you what that means through an example. Assume we have a web page, example.com, that contains this benign script. So the developer assigns a constant object to a property called document.globalconfig. And you see there a property src that contains this benign script, script.js. And then the developer is creating a script tag and setting its src attribute to document.globalconfig.src, and finally adds it to the DOM tree. So who of you think this is vulnerable? I'll give you 5 seconds to think about this. And why? Go ahead and shoot. Well, the title of the slide, I guess, spoils this for you. So this is vulnerable, but basically what's going on is that developer is just writing to a variable and then reading it from the same variable, right? But what if an attacker injects a node that has the same name or ID as the variable that was defined above? So in this case, an image tag with ID global config, then what would happen is that this tag in the DOM tree overshadows the developer-defined variable, so document.globalconfig will now refer to the injected node by the attacker, which has an src attribute called malicious.js, and thereby results in arbitrary client-side code execution without actually injecting any code, but only seemingly benign HTML markups. So to summarize, DOM clobbering is a namespace confusion vulnerability where attackers inject codeless HTML markups and transform this into executable code by exploiting the interactions of the code with the runtime environment. And in this particular case, the markup ID or name collides with sensitive variables or APIs and override their value. OK, so as you've seen in this example, for the DOM clobbering attack, the adversary needs to add codeless pieces of HTML to the DOM tree. And this can happen through injection through one of the input parameters of the program, similarly to the traditional cross-site scripting case, through URL parameters, window name, document refer, post messages, all that. Or it can be done through insertion, and by that I mean by leveraging the application functionalities. So think about code repositories in GitHub or GitLab, where you can write these nice markdown descriptions, which are under the hood converted to HTML. So you're actually inputting HTML. Or web-based text editors, or email clients and messages, posts in CMS-based applications like WordPress, comments, all of those can be HTML. And using this approach, attackers can also implant persistent DOM clobbering payload into web applications, which can lie dormant and exploited later on to attack a victim. Now, DOM clobbering, why does this happen? The answer to this question lies in how elements are located in the DOM tree. And there are actually two ways to do this. I'll call it the dirty way and the clean way. The clean way is to use DOM query selectors, and the dirty way is a property access on window or document object. And to clarify this, let's have a look at this simple example. So we have an HTML document that contains a form with name X, and then two children input with ID Y and input with ID Z. And let's say the developer wants to select the node N5 in this DOM tree. So the clean way would be to write document.querySelector ID equal Y in JavaScript to get this node, versus the dirty way, the developer can write document.x to first get the form object, and because the form object has a children with ID Y, then document.x.y will return N5, or it can simply write window.y. And this rule is basically known as named access on the window or document object in the HTML specification. And DOM clobbering exploits such rules. So why is this important? Unfortunately, according to the Google Chrome telemetry data, clobbered variable access usages are used in 11% of the web pages in the wild, and we cannot simply turn this feature off because seemingly it will cause a lot of breakage. And if we don't turn this off, it will cause vulnerabilities in web applications. And here you see an example of a DOM clobbering attack in Gmail in 2019. So Gmail has this feature called dynamic mail that allow you to include in your email not only static content like images and some text, but also interactive forms and scripts. And because the source code of Gmail actually had dynamically created a script whose src value at the end of the day came from a variable called window.test location, and it was possible to clobber these src attribute with a seemingly benign codeless markup, and the sanitizer of Gmail, AMP4 email, did not actually block this markup because it does not contain any JavaScript code. It's a benign markup. And this results in arbitrary client-side code execution. Fortunately, Gmail had secure CSP, so loading code from a third-party domain was not possible here. So it was not possible to exploit this vulnerability. OK, so now that we have the necessary background on DOM clobbering, let's dive into the details. In this talk, we'll go over clobbering markups and browser behaviors on DOM clobbering, vulnerability detection and prevalence, so how to actually automatically detect these vulnerabilities, and how prevalent are DOM clobbering vulnerabilities in the wild. In turn, we'll have a look at existing countermeasures and how effective are they against DOM clobbering. OK, so our knowledge about DOM clobbering vulnerabilities is very limited, despite the fact that DOM clobbering is known for more than a decade ago. And they first affected frame-busting codes in web applications. And those are essentially assignments like top.location equal self.location. And back then, attackers could have used an iframe named self to clobber and override the top window location of web pages, achieving cross-site scripting or open redirections. And one important question here is, what other attack markups will work in addition to an iframe named self? Now, to answer this research question, we first have to answer what types of variables and attackers can overwrite in the JavaScript domain. So there could be different targets, and these targets could be custom symbols, like custom JavaScript variables, or they can be built-in APIs in the DOM tree, like the self in the previous example. So if they are custom symbols, they can, of course, be variables or globals, meaning properties of the window and document object, or they can be object properties like x.y, window.x.y, and so on. And built-in DOM APIs can be methods. So for instance, window.addEventListener, or they can be properties. For instance, document.documentURI, which returns the URL of the web page, or document.title, which returns the title of the web page, or window.caches, which is basically the cache storage. Now, not all of these built-in DOM APIs can be successfully overshadowed because there are protection mechanisms against clobbering them in browsers. So for instance, we have document.documentURI, which can be successfully clobbered in most browsers with an iframe named documentURI. But you cannot clobber document location in any browsers today. Because if you can do that, you can set a JavaScript URI and achieve cross-site scripting. Now, the challenge is this can also be browser dependent, and we also tested different DOM APIs that we have across different browsers. And interestingly, for instance, we observed that a property like window.crossOriginIsolated, you can clobber this in most of the iOS-based browsers and also the UC browser in Android, but not, for instance, in Chromium-based browsers in desktop and Android. And in general, we found that there are also security-sensitive APIs that you can clobber, such as trusted types and cache storage. OK, so the next question is, now that we know what to clobber, the next question is how to clobber, actually. And for this, attackers abuse the standard or HTML and DOM specification rules. And there are a variety of these rules. So I already showed you one rule, which is named access on the window. But combining these rules, attackers can clobber and override these variables. So let me show you an example. Assume we want to clobber window.x.y. Attackers can combine the rule 1, named access on window, and form parent-child to basically clobber this. So first, they add a form with ID equal x, which clobbers window.x. And then to go from window.x to window.x.y, they have an input with name y as a children of the form. So this way, they can access nested properties. Another alternative is to combine, again, rule 1 with the HTML collection rule, which basically says that if two tags in the DOM tree have the same ID, so in this particular example, we have two anchor tags with ID X, then they form an array-like object called HTML collections. So this way, we have an HTML collection, and to refer to a particular node, the second element can have a name property. Again, this allows you to clobber window.x.y. And there are also other combinations of these rules that can allow you to clobber different things, for instance, document properties. Now, the real thing that we want to answer is, how do we automatically detect all these combinations? Because, of course, you can manually go and find some of these cases, but it would be very nice if we can automatically find all DOM clobbering markups and cases in different browsers. So to do that, we basically reviewed HTML specifications and past instances of DOM clobbering attacks. Then we derive markup generation rules by analyzing how DOM clobbering markups work. And then we test these markups in various mobile and desktop browsers. So to give you an example how this works, let's start from our previous HTML collection example, where you have an anchor tag with this, two anchor tags with the same ID. And let's say our clobbering target is again the same. So here we can mutate the tags, attributes, relationships in attack targets. So we can change the anchor tag to a div tag, or we can change the ID to name, or we can, instead of value ID equal X, we can have ID equal Y, or the relationship, instead of being two siblings, one can be the children of the other one, or one can be an attribute value of the other one. And by combining all these mutations automatically, we can generate candidate markups and then feed them to test pages, to browsers, and see which ones will be successfully clobbered and working. So in total, we generated 24 million test cases, and we tested them in 19 different browsers, and the results were alarming. We discovered over 31.4K distinct DOM clobbering markups that work across 5 different techniques. And of these, only 481 were previously known. An example of these, which is new, is an HTML collection. So for instance, you can use certain combinations of tags with the same name to, again, form an HTML collection, while in the specification, it's only with the ID. So 2 object tags with the same name can form an HTML collection. So for more details about these clobbering markups, please feel free to refer to our paper. And we also have an online markup generator service that you can specify your clobbering target and clobbering value, and we'll suggest you clobbering markups. So this is accessible on our website, domclob.xyz. And this brings us to the question, how do browsers behave? Well, not sure if inconsistently consistent or consistently inconsistent, because for the 31.4K markups, in 31.2 of them, meaning the majority, there is at least one browser that disagrees with others. And this actually makes defending increasingly more challenging for developers. Fortunately, these differences and inconsistencies, in total, there are 10 distinct behavioral groups. And in the figure, you see the ones that have the same behavior in color. And it is insane that the ones that are in mark are mainly iOS-based browsers, and each of them have a different behavior. So no 2 browsers in iOS behave the same, which is insane. And in this case, the highest amount of risk is associated with Chromium-based browsers, in which 59 classes of DOM clobbering markups work, whereas the lowest amount of risk is associated with Firefox-based browsers in desktop and Android, and of course the Tor browser, in which only 35 classes of DOM clobbering markups work. And again, we have an online browser testing service available on our website, where you can check if certain DOM clobbering markups works in your browser or not. OK, now let's look at automatic vulnerability detection and prevalence to see how bad is the situation. Now, we proposed an open source static dynamic tool for detecting DOM clobbering vulnerabilities at scale. And at a high level, our tool has 3 components: data collection, vulnerability analysis, and verification. So the data collection module contains a Chrome-based crawler based on Puppeteer and DevTools protocol that, given a single seed URL of the application under test, collects the web page resources and scripts. Then, given these web pages, the set of syncs and the clobberable built-in APIs that we found from part 1 of our study, we essentially model the web page as a property graph, and then we can traverse this graph for discovery of clobberable data flows. And here, contrary to the traditional taint analysis, not all DOM clobbering sources are a predefined syntactic object, but also they can be a specific property of the program. In a sense, this is essentially a data flow task, but 2 data flow tasks. One, to understand which variables are undefined in certain execution context. And second, if there is a data flow from DOM clobbering sources to security-sensitive things. So this module will output the candidate data flows detected by the static analyzer. And finally, we can confirm this dynamically with force execution and dynamic taint analysis in a specific browser. Now you can access our tool on joe.me. And we essentially use this tool to conduct an empirical study to quantify the prevalence of DOM clobbering vulnerabilities in the wild. So we tested the Tranco top 5,000 websites, processing in total over 24 billion lines of JavaScript code and over 200,000 web pages. And our results were, again, alarming. We detected over 9,400 clobberable data flows in 491 affected websites. And these, out of these, we created actual exploits for 44 websites, all of which were confirmed and patched, including GitHub, Trello, Vimeo, Fandom, and other popular websites. And these essentially allowed attackers to obtain client-side cross-site scripting, open redirection, and request forgery attacks. So let me show you an example. So this example actually affects GitHub. And to understand how this works, we have to know first what is double DOM clobbering trick. So basically assume we have a web application that has 2 scripts. In the first script, you have a built-in API, which is clobberable in a certain browser. And then the same script basically creates a variable on window or document, and then assigns it to a constant value. And then the second script actually reads that value, which was defined in the first script. So what happens is that if an attacker clobbers this native API, which is a method, then that method from then onwards will refer to a node in the DOM tree, which is not a function. So because this is not a function anymore, this will cause a breakage in the first script. The browser will stop parsing the rest of the script. So the variable that the developer defined will actually go undefined. And because this is undefined, then in the second script, window.var1 can now be clobbered. And essentially, attackers can clobber these by injecting 2 different payloads. So in the case of GitHub, there was a function @evenListener, which is clobberable in the first script. And then there was a variable called boomr, which is for loading the Akamai Boomerang library. And attackers could have clobbered this by just having an image tag with name @evenListener. And there was this second script that essentially dynamically creates a script, sets its src to window.boomr.url, and then adds it to the DOM tree. And it was possible to clobber this with HTML collections. So we basically create 2 anchor tags with ID boomr, and the second one has a name attribute URL and an href attribute malicious.js. So this way, attackers can overwrite window.boomr.url, resulting in arbitrary code execution. And this brings us to existing defenses and their effectiveness. So now that I convince you DOM clobbering is a prevalent issue, how do we defend against it, actually? So one obvious mitigation technique, as we also seen in the previous talk, is content security policy. Developers can use a script SRC to constrain script sources to a set of trusted domains, preventing the clobbering of the SRC attribute, for instance, in the GitHub or Gmail example. However, this does not work in case attackers can clobber parameters of dynamic code evaluation functions like eval, new function, and set timeout. And unfortunately, 85% of the vulnerabilities in our dataset cannot be mitigated by CSP because they were abusing this second case. An alternative solution is to freeze DOM objects with the object.freeze API, which prevents objects in JavaScript to be overwritten by named DOM elements. However, this is also in practice very difficult to roll out because developers need to know, first of all, which variables they need to freeze and which object properties they need to freeze. Second, it is ineffective when the DOM clobbering source is a built-in API because those cannot be frozen. And this means that, again, around 21% of the vulnerabilities in our dataset cannot be mitigated by object freezing, even if the developer correctly finds and freezes the objects that needs to be freezed. And a more feasible, more practical solution is HTML sanitization. So we evaluated the robustness of 29 client-side and server-side HTML sanitizers across the top 5 web programming languages. And what we did was basically input the 31,000 clobbering markups that we identified in the first part of our study to these sanitizers, and check whether the sanitizer removes or changes named properties, in particular ID and name attributes. And we tested these sanitizers under 2 configurations. First, the default configuration of the sanitizer, and second, the most strict configuration that the sanitizer provides. And what we discovered was that in total, 16 sanitizers were vulnerable to at least one clobbering markup in their default setup. And this includes the popular sanitizers like DOM-Purify, Mozilla, Bleach, and Google Kafka. And 13 of these 16 sanitizers, interestingly, were also vulnerable in their most strict configuration. On the other hand, the other 13 sanitizers were not vulnerable, but they always removed named properties. And this includes cases that do not even lead to DOM clobbering, for example, an anchor tag with the name property. And this may interfere with cases where developers actually need those attributes. So this can have usability issues. So the alternative solution to removing these name properties that we proposed is namespace isolation. And what that means is basically we can prefix name properties with a constant string, say const. This mitigates almost all DOM clobbering cases, but it requires some implementation change by developers in their application logic. And we actually implemented namespace isolation in the famous DOM-Purify sanitizers. So now DOM-Purify has a flag called sanitize named props that essentially hardens the existing DOM clobbering protection of DOM-Purify. And if you want to learn more about this, please feel free to check out the GitHub pull request. And finally, there is also a kill switch, which is disabling DOM clobbering in browser level, or in particular, disabling name properties at browser level. So this fixes all DOM clobbering cases, but as I also showed you, with the Google Chrome telemetry data, this can cause breakage, and apparently significant breakage. So we conducted a measurement to understand what amount of web pages in the wild will break. So we discovered the same number, 13.3%, which is in line with the number in the Google Chrome telemetry data. But interestingly, these 13% were scattered over 51% of the sites. So this means if you disable these, half of the web will break, essentially. And well, as the benefit, you will fix the 491 vulnerable sites, which is about 10% of the top 5K sites. And then again, this brings us to the breakage benefit balance of a ratio of 5:1, meaning per 1 vulnerable sites that you fix, you will break actually 5 of them, which means this approach is not feasible, for sure. So that's why we actually proposed to W3C to have an opt-in CSP or permission policy flag to allow developers to optionally disable name properties if they don't want to actually use this feature. So they can disable this. And there is a whole discussion going on in W3C about this, but in the thread, it seems that we are the only ones believing this is a good idea, mainly because it has major implementation efforts for browser vendors to create such a binary flag that disables suddenly all clobbering of via name properties. Okay, so now none of these defenses and countermeasures that we have are bulletproof. What can we do about this? So we can identify existing vulnerable patterns in the wild, and we can tell developers about them. So we characterize the vulnerabilities that we had in our data set based on their high-level syntax and semantics, and we identified 8 common patterns. So here I will show you 3 of these patterns. In the first example, the developer is accessing a property of window and then putting it in a sink. The second example, the developer accessing an API from window or document and then again putting it in a sink. And the third example is actually similar to the first example of DOM clobbering that we saw. The developer assigns something to the document object and later read from the document object. And to fix these cases, we only need very simple approaches. So we can have explicit variable declarations to fix the first pattern. The developers need to just have a variable defined with the var declarator, which prevents the clobbering of window.var because var is not undefined anymore in that execution context. We can have a strict type checking because when you clobber a variable, it will point to a node in the DOM tree or an HTML element. So by checking whether a native API is not an instance of a HTML element, we can make sure if that is not clobbered. Or by not using, in general, document and window for storing global variables. Instead, we can just rely on constant variables or variable declarations. Now, we incorporated these guidelines and many more others into the OWASP cheat sheet series. So feel free to scan this QR code and check out some of the guidelines that we have out there. And you can also check out other patterns that we have in our paper in Auckland to learn more about common mistakes developers make. Okay, so what did we learn in this study? First, DOM clobbering markups come in many forms and variants, and there are over 31,000 of them. Second, DOM clobbering is ubiquitous in the wild, affecting 9.8% of the website in the wild, so this has to be taken seriously. And third, existing defenses and current countermeasures that we have are helpful, but may not completely cut it. So thanks a lot for your attention, and if you have any questions, please don't hesitate to ask.